Good evening, friends, and welcome to Sleepy Time Tales, a podcast aimed at helping you to get a good night's sleep. Do you find your mind troubled with the stresses of modern life, especially when the lights are out and you're trying to get a restful night? Does your spinning mind keep you awake? Follow my voice down the path towards a good night's rest. Listen to me tell a story that will keep your mind from wandering to your daytime problems. Ones you can't solve right now and will be easier to solve well rested. Listen to my voice and allow yourself to drift, following the twists and turns of the story, but slowly letting go and drifting into sleep. Let my voice wash over you at a comfortable volume and allow yourself to be distracted from the stresses and worries that play on your mind. Whether you need help falling asleep or going back to sleep in the middle of the night, you can trust me to keep you company and help you to wake up tomorrow in a rested state. You may need to try out Sleepy Time Tales for a few nights to get used to this slightly strange idea, but I believe it will be well worth your while. I'm here to work with you, to create a safe space, a cocoon in which you can curl up and allow nature to take its course. So settle down, relax, and allow yourself to get lost in my telling of tonight's story. Before we get to tonight's reading, I'd like to ask for a few minutes of your time. Sleepy Time Tales is a listener-supported podcast. I can only keep it going, paying for the services and tools that I use, and justify the time that on it thanks to the generosity of folks like you. So if you're finding Sleepy Time Tales useful, if it helps you to get a restful night, and you'd like to help keep it going out to thousands of other insomniacs, please consider supporting it on the Patreon at patreon.com/sleepytimetales. This is monthly support that helps me keep the lights on and gets you fun bonuses based on your contribution level. So go along there, take a look, and sign up if you're interested. And if monthly seems like a big ask, which I can completely understand, you can also make once-off tips to the tip jar on the website. And if you'd like to help Sleepy Time Tales out without having to do so financially, you can just spread the word. Whether in person or on social media, if you know someone who's struggling to sleep and you think that listening to this little old podcast will help, just let them know. Now that's enough of that. Let's get on with learning more about the mechanisms of erosion. We return this week to The Elements of Geology by Harmon Norton. And we carry on learning about the role of rivers in geology. Deltas. In the river deposits which are left above sea level, particles of waste are allowed to linger only for a time. From alluvial fans and floodplains, they are constantly being taken up and swept further on downstream. Although these landforms may long persist, the particles which compose them are ever-changing. We may therefore think of the alluvial deposits of a valley as a stream of waste fed by the waste mantle, as it creeps and washes down the valley sides, and slowly moving onwards to the sea. In basins, waste finds a longer rest, but sooner or later lakes and dry basins are drained or filled, and the deposits, if above sea level, resume their journey to their final goal. It is only when carried below the level of the sea that they are indefinitely preserved. On reaching this terminus, rivers deliver their load to the ocean. In some cases, the ocean is able to take it up by means of strong tidal and other currents, and to dispose of it in ways which we shall study later. But often the load is so large or the tides are so weak that much of the waste which the river brings in settles at its mouth, there building up a deposit called the delta, from the Greek letter of that name, whose shape it sometimes resembles. Deltas and alluvial fans have many common characteristics. Both owe their origin to a sudden check in the velocity of the river, compelling a deposit of the load. Both are triangular in outline, the apex pointing upstream, and both are traversed by distributaries which build up in all parts in turn. In a delta, we may distinguish deposits of two distinct kinds. the submarine and the subaerial. In part, a delta is built of waste brought down by the river and redistributed and spread by waves and tides over the sea bottom adjacent to the river's mouth. The origin of these deposits is recorded in the remains of marine animals and plants which they contain. As the marine delta grows near to the level of the sea, the distributaries of the river cover it with subaerial deposits, altogether similar to those of the floodplain, of which indeed the subaerial delta is the prolongation. Here extended deposits of peat may accumulate in swamps, and the remains of land and freshwater animals and plants swept down by the stream are embedded in the silts laid at the times of flood. Borings made in the deltas of great rivers such as the Mississippi, the Ganges, and the Nile show that the subaerial portion often reaches a surprising thickness. Layers of peat, old soils, and forest grounds with the stumps of trees are discovered hundreds of feet below sea level. In the Nile Delta, some 8 layers of coarse gravel were found interbedded with river silts, and in the Ganges Delta at Calcutta, a boring nearly 500 feet in depth stopped in such a layer. The Mississippi has built a delta of 12,300 square miles and is pushing the natural embankments of its chief distributaries into the Gulf at a maximum rate of a mile in 16 years. Muddy shoals surround its front. Shallow lakes, for example Lakes Pontchartrain and Bourne, are formed between the growing delta and the old shoreline, and elongate lakes and swamps are enclosed between the natural embankments of the distributaries. The delta of the Indus River, India, lies so low along shore that a broad tract of country is overflowed by the highest tides. The submarine portion of the delta has been built to near sea level over so wide a belt offshore that in many places large vessels cannot come even within sight of land because of the shallow water. A former arm of the sea, the Ran of Kush, adjoining the delta on the east, has been salted up and is now an immense barren flat of sandy mud, 200 miles in length and 100 miles in greatest breadth. Each summer it is flooded with salt water when the sea is brought in by strong southwesterly monsoon winds, and the climate during the remainder of the year is hot and dry. By the evaporation of seawater, the soil is thus left so salty that no vegetation can grow up on it, and in places beds of salt several feet in thickness have accumulated. Under like conditions, salt beds of great thickness have been formed in the past, and are now found buried among the deposits of ancient deltas. Subsidence of great deltas. As a rule, great deltas are slowly sinking. In some instances, upbuilding by river deposits has gone on as rapidly as the region has subsided. The entire thickness of the Ganges Delta, for example, so far as it has been sounded, consists of deposits laid in open air. In other cases, interbedded limestones and other sedimentary rocks, containing marine fossils, prove that at times subsidence is gained on the upbuilding, and the delta has been covered with the sea. It is by gradual depression that delta deposits attain enormous thickness, and being lowered beneath the level of the sea are safely preserved from erosion, until a movement of the Earth's crust in the opposite direction lifts them to form part of the land. We shall read later in the hard rocks of our continent the records of such ancient deltas, and we shall not be surprised to find them as thick as those that are now building at the mouths of great rivers. Lake deltas. Deltas are also formed where streams lose their velocity on entering the still waters of lakes. The shorelines of extinct lakes, such as Lake Agassiz and Lakes Bonneville and Lahontan, may be traced by the heavy deposits at the mouths of their tributary streams. We have seen that the work of streams is to drain the lands of water poured upon them by rainfall, to wear them down and to carry their waste away to the sea, there to be rebuilt by other agents into sedimentary rocks. The ancient strata of which the continents are largely made are composed chiefly of material thus worn from still more ancient lands with their hills and valleys like those of today, and carried by the rivers to the ocean. In all geological times, as at the present, the work of streams has been to destroy the lands, and in so doing to furnish to the ocean the materials from which the lands of future ages were to be made. Before we consider how the waste of the land brought in by streams is rebuilt upon the ocean floor, we must proceed to study the work of two agents, glacier ice and the wind, which cooperate with rivers in the denudation of the land. Chapter 5. The work of glaciers. The drift. The surface of northeastern North America, as far south as the Ohio and Missouri rivers, is generally covered by the drift, a formation which is quite unlike any which we have so far studied. A section of it, such as that illustrated in Figure 87, shows that for the most part it is unstratified, consisting of clay and pebbles and even large boulders, all mingled pell-mell together. The agent which laid the drift is one which can carry a load of material of all sizes, from the largest boulder to the finest clay, and deposit it without sorting. The stones of the drift are of many kinds. The region from which it was gathered may well have been large in order to supply these many different varieties of rocks. Pebbles and boulders have been left far from their original homes, as may be seen in southern Iowa, where the drift contains nuggets of copper brought from the region about Lake Superior. The agent which laid the drift is one able to gather its load over a large area and carry it a long way. The pebbles of the drift are unlike those rounded by running water or by waves. They are marked with scratches. Some are angular, many have had their edges blunted, while others have been ground flat and smooth on one or more sides, like gems which have been faceted by being held firmly against the lapidary's wheel. In many places, the upper surface of the country rock beneath the drift has been swept clean of residual clays and other waste. All rock rotten has been planed away, and the ledges of sound rock to which the surface has been cut down have been rubbed smooth and scratched with long, straight, parallel lines. The agent which laid the drift can hold sand and pebbles firmly in its grasp, and can grind them against the rock beneath, thus planing it down and scoring it, while faceting the pebbles also. Neither water nor wind can do these things. Indeed, nothing like the drift is being formed by any process now at work anywhere in the eastern United States. To find the agent which has laid this extensive formation, we must go to a region of different climatic conditions. The inland ice of Greenland. Greenland is about 1,500 miles long, and nearly 700 miles in greatest width. With the exception of a narrow fringe of mountainous coastland, it is completely buried beneath a sheet of ice, in shape like a vast white shield, whose convex surface rises to a height of 9,000 feet above the sea. The few explorers who have crossed the ice cap found it a trackless desert destitute of all life, save such lowly forms as the microscopic plant which produces the so-called red snow. On the smooth plain of the interior, no rock waste relieves the snow's dazzling whiteness. No streams of running water are seen. The silence is broken only by the howling storm winds and the rustle of the surface snow which they drive before them. Sounding with long poles, explorers find that below the powdery snow of the latest snowfall lie successive layers of earlier snows, which grow more and more compact downward, and at last have altered to impenetrable ice. The ice cap formed by the accumulated snows of uncounted centuries may well be more than a mile in depth. Ice thus formed by the compacting of snow is distinguished when in motion as glacier ice. The inland ice of Greenland moves. It flows with imperceptible slowness under its own weight, like a mass of some viscous or plastic substance, such as pitch or molasses candy, in all directions outward toward the sea. Near the edge it is so thinned that mountain peaks are laid bare. These islands in the sea of ice being known as the Nunataks. Down the valleys of the coastal belt it drains in separate streams of ice or glaciers. The largest of these reach the sea at the head of inlets, and are therefore called tide glaciers. Their fronts stand so deep in seawater that there is visible seldom more than 300 feet of the wall of ice, which in many glaciers must be 2,000 and more feet high. From the sea walls of tide glaciers, great fragments break off and float away as icebergs. Thus, snows which fell on the interior of this northern land, perhaps many thousands of years ago, are carried in the form of icebergs to melt at last in the North Atlantic. Greenland, then, is being modelled over the vast extent of its interior, not by streams of running water, as are regions in warm and humid climates, nor by currents of air, as are deserts to a large extent, but by a sheet of flowing ice. What the ice sheet is doing in the interior we may infer from a study of the separate glaciers into which it breaks at its edge. The smaller Greenland glaciers. Many of the smaller glaciers of Greenland do not reach the sea, but deploy on plains of sand and gravel. The edges of these ice tongues are often as abrupt as if sliced away with a knife, and their structure is thus readily seen. They are stratified, their layers representing in part the successive snowfalls of the interior of the country. The upper layers are commonly white and free from stones, but the lower layers, to the height of 100 feet or more, are dark with debris which is being slowly carried on. So thickly studded with stones is the base of the ice that it is sometimes difficult to distinguish it from the rock waste which has been slowly dragged beneath the glacier, or left about its edges. The waste beneath and about the glacier is unsorted. These stones are of many kinds, and numbers of them have been found ground to flat faces. Where the front of the ice has retreated, the rock surface is seen to be planed and scored in places by the stones frozen fast in the soul of a glacier. We have now found in glacier ice an agent able to produce the drift of North America. The ice sheet of Greenland is now doing what we have seen was done in the recent past in our own land. It is carrying for long distances rocks of many kinds gathered, we may infer, over a large extent of country. It is laying down its load without assortment in unstratified deposits. It grinds down and scores the rock over which it moves, and in the process many of the pebbles of its load are themselves also ground smooth and scratched. Since this work can be done by no other agent, we must conclude that the northeastern part of our own continent was covered in the recent past by glacier ice, as Greenland is today. Valley glaciers. The work of glacier ice can be most conveniently studied in the separate ice streams which creep down mountain valleys in many regions such as Alaska, the western mountains of the United States and Canada, the Himalayas and the Alps. As the glaciers of the Alps have been studied longer and more thoroughly than any others, we shall describe them in some detail as examples of valley glaciers in all parts of the world. Conditions of glacier formation. The condition of the great accumulation of snow to which glaciers are due, that more or less of each winter snow should be left over unmelted and unevaporated to the next, is fully met in the Alps. There is abundant moisture brought by the winds from neighboring seas. The currents of moist air driven up the mountain slopes are cooled by their expansion as they rise, and the moisture which they contain is condensed at a temperature at or below 32 degrees Fahrenheit, and therefore is precipitated in the form of snow. The summers are cool, and their heat does not suffice to completely melt the heavy snow of the preceding winter. On the Alps, the snow line, the lower limit of permanent snow, is drawn at about 8,500 feet above sea level. Above the snow line on the slopes and crests, where these are not too deep, the snow lies the year round, and gathers in valley heads to a depth of hundreds of feet. This is but a small fraction of the thickness to which snow would be piled on the Alps, were it not constantly being drained away. Below the snowfields which mantle the heights, the mountain valleys are occupied by glaciers, which extend as much as a vertical mile below the snow line. The presence in the midst of forests and meadows and cultivated fields of these tongues of ice, ever melting, and yet from year to year using none of their bulk, proves that their loss is made good in the only possible way. They are fed by snow fields above, whose surplus of snow they drain away in the form of ice. The presence of glaciers below the snow line is a clear proof that, rigid and motionless as they appear, glaciers really are in constant motion down valley. The Neve Field. The head of an alpine valley occupied by a glacier is commonly a broad amphitheatre deeply filled with snow. Giant peaks tower above it, and snowy slopes rise on either side on the flanks of mountain spurs. From these heights, fierce winds drift the snows into the amphitheatre, and avalanches pour in their torrents of snow and waste. The snow of the amphitheatre is like that of drifts in late winter after many successive thaws and freezings. It is made of hard grains and pellets and is called neve. Beneath the surface of the neve field and at its outlet, the granular neve has been compacted to a mass of porous crystalline ice. Snow has been changed to neve, and neve to glacial ice, both by pressure, which drives the air from the interspaces of the snowflakes, and also by successive meltings and freezings, much as a snowball is packed in the warm hand and becomes frozen to a ball of ice. The Berggrund. The neve is in slow motion. It breaks itself loose from thinner snows around it, too shallow to share its motion, and from the rock rim which surrounds it, forming a deep fissure called the Berggrund, sometimes a score or more feet wide. Size of glaciers. The ice streams of the Alps vary in size according to the amount of precipitation and the area of the neve fields which they drain. The largest of alpine glaciers, the Aletsch, is nearly 10 miles long and has an average width of about a mile. The thickness of some of the glaciers of the Alps is as much as 1,000 feet. Giant glaciers more than twice the length of the longest in the Alps occur on the south slope of the Himalaya Mountains, which receive frequent precipitations of snow from moist winds from the Atlantic Ocean. The best known of the many immense glaciers of Alaska, the Muir, has an area of about 800 square miles. Glacier motion. The motion of the glaciers of the Alps seldom exceeds 1 or 2 feet a day. Large glaciers, because of the enormous pressure of their weight, and because of less marginal resistance, move faster than small ones. The Muir advances at the rate of 7 feet a day, and some of the larger tide glaciers of Greenland are reported to move at the exceptional rate of 50 feet and more at the same time. Glaciers move faster by day than by night, and in summer than in winter. Other laws of glacier motion may be discovered by a study of figures 96 and 97. It is important to remember that glaciers do not slide bodily over their beds, but urged by gravity more slowly down valley in somewhat the same way as would a stream of thick mud. Although small pieces of ice are brittle, the large mass of granular ice which composes a glacier acts as a viscous substance. Crevices. Slight changes of slope in the glacier bed and the different rates of motion in different parts produce tensions under which the ice cracks open, and opens in great fissures called crevices. At an abrupt descent in the bed, the ice is shattered into great fragments, which unite again below the icefall. Crevices are opened on lines at right angles to the direction of the tension. Transverse crevices are due to a convexity in the bed which stretches the ice lengthwise. Marginal crevices are directed upstream and inwards. Radial crevices are found where the ice stream deploys from some narrow valley and spreads upon some more open space. What is the direction of the tension which causes each, and to what is it due? Lateral and medial moraines. The surface of a glacier is striped lengthwise by long, dark bands of rock debris. Those in the center are called the medial moraines. The one on either margin is a lateral moraine and is clearly formed of waste which has fallen on the edge of the ice from the valley slopes. A medial moraine cannot be formed in this way, since no rock fragments can fall so far out from the sides. But following it up the glacial stream, one finds that a medial moraine takes its beginning at the junction of the glacier and some tributary and is formed by the union of their two adjacent lateral moraines. Each branch thus adds a medial moraine. By counting the number of medial moraines of a trunk stream, one may learn of how many branches it is composed. Surface moraines appear in the lower course of the glacier as ridges, which may reach the exceptional height of 100 feet. The bulk of such a ridge is ice. It has been protected from the sun by the veneer of moraine stuff, while the glacier surface on either side is melted down at least the distance of the height of the ridge. In summer, the lowering of the glacial surface by melting goes on rapidly. In Swiss glaciers, it has been estimated that the average lowering of the surface by melting and evaporation amounts to 10 feet a year. As a moraine ridge grows higher and more steep by the lowering of the surface of the surrounding ice, the stones of its cover tend to slip down its sides. Thus, moraines broaden until near the terminus of a glacier they may coalesce into a wide field of stony waste. In glacial drift, this name is applied to whatever debris is carried within the glacier. It consists of rock waste fallen on the neve, and there buried by the accumulations of snow and of that engulfed in the glacier, where crevices have opened beneath the surface moraine. As the surface of the glacier is lowered by melting, more or less in glacial drift is brought again to open air, and near the terminus it may help to bury the ice from view beneath a sheet of debris. The ground moraine. The drift dragged along at the glacier's base and lodged beneath it is known as the ground moraine. Part of the material of it has fallen down deep crevasses, and part has been torn and worn from the glacier's bed and banks. While the stones of the surface moraines remain as angular as when they lodged on the ice, many of those of the ground moraine have been blunted on the edges and faceted and scratched by being ground against one another and the rocky bed. In glaciers such as those of Greenland, whose basal layers are well loaded with drift, and whose surface layers are nearly clean, different layers have different rates of motion, according to the amount of drift with which they are clogged. One layer glides over another, and the stones inset in each are ground and smoothed and scratched. Usually the sides of glaciated pebbles are more worn than the ends, and the scratches upon them run with the longer axis of the stone. Why? The terminal moraine. As a glacier is in constant motion, it brings to its end all of its load, except such parts of the ground moraine as may find permanent lodgment beneath the ice. Where the glacier front remains for some time at one place, There is formed an accumulation of drift known as a terminal moraine. In valley glaciers, it is shaped by the ice front to a crescent, whose convex side is downstream. Some of the pebbles of the terminal moraine are angular, and some are faceted and scored, the latter having come by the hard road of the ground moraine. The material of the dump is for the most part unsorted, though the water of the melting ice may find opportunity to leave patches of stratified sands and gravels in the midst of the unstratified mass of drift, and the finer material is in places washed away. Glacier drainage. The terminal moraine is commonly breached by a considerable stream, which issues from beneath the ice by a tunnel, whose portal has been enlarged to a beautiful archway by melting in the sun and the warm air. The stream is grey with silt and loaded with sand and gravel washed from the ground moraine. Glacier milk, the Swiss call this muddy water, the grey colour of whose silt proves its rock flour freshly ground by the ice from the unoxidized sound rock of its bed. The mud of streams being yellowish when it is washed from the oxidized mantle of waste. Since glacial streams are well loaded with waste due to vigorous ice erosion, and the valley in front of the glacier is commonly aggraded to a broad, flat floor, these outwash deposits are known as valley drift. The sand brought out by streams from beneath the glacier differs from river sand, and it consists of freshly broken angular grains. Why? The stream derives its water chiefly from the surface melting of the glacier. As the ice is touched by the rays of the morning sun in summer, water gathers in pools and rills trickle and unite in brooklets which melt and cut shallow channels in the blue ice. The course of these streams is short. Soon they plunge into deep wells cut by their whirling waters where some crevasses have begun to open across their path. These wells lead into chambers and tunnels by which sooner or later their water finds way to the rock floor of the valley, and they unite in a subglacial stream. The lower limit of glaciers. The glaciers of a region do not by any means end at a uniform height above sea level. Each terminates where its supply is balanced by melting. Those, therefore, which are fed by the largest and deepest neaves, and those also which are best protected from the sun by a northward exposure, or by the depth of their enclosing valleys, flow to the lower levels, than those whose supply is less, and whose exposure to the sun is greater. A series of cold, moist years with abundant snowfall causes glaciers to thicken and advance. A series of warm, dry years causes them to wither and melt back. The variation in glaciers is now carefully observed in many parts of the world. The Moya glacier has retreated 2 miles in 20 years. The glaciers of the Swiss Alps are now for the most part melting back, although a well-known glacier of the Eastern Alps, the Vernacht, advanced 500 feet in the year 1900, and was then ploughing up its terminal moraine. How soon would you expect a glacier to advance after its knee fields have been swollen with unusually heavy snows, as compared with the time needed for the flood of a large river to reach its mouth after heavy rains upon its headwaters? On the surface of glaciers in summertime, one may often see large stones supported by pillars of ice several feet in height. These glacier tables commonly slope more or less strongly to the south, and thus may be used to indicate roughly the points of the compass. Can you explain their formation and the direction of their slope? On the other hand, a small and thin stone or a patch of dust lying on the ice tends to sink a few inches into it. Why? In what respects is a valley glacier like a mountain stream which flows out upon desert plains? Two confluent glaciers do not mingle their currents as do two confluent rivers. What characteristics of surface moraines prove this fact? What effect would you expect the laws of glacier motion to have on the slant of the sides of transverse crevasses? A trunk glacier has 4 medial moraines, of how many tributaries is it composed. Illustrate by diagram. State all the evidences which you have found that glaciers move. If a glacier melts back with occasional pauses up a valley, what records are left of its retreat? And before we carry on with other forms of glaciers, I'm going to call it a night. As always, if you want to pick up where I'm leaving off, you can find the original on Project Gutenberg at the link in the show notes. Thanks again for joining me on this episode of Sleepy Time Tales, the podcast designed around a bedtime story to help you to get a restful night. New episodes will be released every Sunday night to give you something fresh to help you rest in a new week. But make sure to follow or subscribe in whatever service you use so that you get your new episodes whenever they come out. Good night and sweet dreams.